I'm Adrienne. I will be presenting our work, Morpho-syntactic lexical generalization for CCG semantic parsing. This is a collaborative work done with Kwiatkowski and my advisor, Zettlemoyer at University of Washington. Sorry. So semantic parsing in general is a task of recovering meaning representation from natural language text. So given a set of sentences like this, we build a semantic parser that maps from the sentence to their logical expression. And there could be many language understanding tasks that can use a logical expression, and one possible downstream application could be just to query the database and then get a set of answers. So here that we show a standard setup for learning a semantic parser using the CCG approach. So the training set contains a set of sentences paired with their full meanings, but we're only illustrating the sentences here. So the key problem is to induce a CCG lexicon, which represent the meaning of each word and phrase that shows in the training set, and later at test time, that they are combined to generate new meanings. So this is how the typical CCG lexicon looks like, that it learns a separate entry for each word and phrase, and we're going to demonstrate later that this representation has flaws and then can potentially cause problem when you see new sentences. So let's try to parse these sentences using the lexicon that's learned directly from the training set. So in case number 1, there is no hope in recovering the meaning of this sentence because the grammar suffers from data sparsity. So we can possibly learn the meaning of departing because we've seen the exact word in the training set, but arriving has never appeared anywhere in the training set in the exact ing form. So in case number 2, the word departure has only appeared once in the entire training set. For rarely seen words like departure, it's very possible that we can learn some very special case, complex lexical entry that sort of managed to fit in the specific syntactic context of the training sentence, but they're not going to generalize well at test time. So, but remember that languages are constructed based on certain principles and then processes. So these error cases motivate us to design a lexicon induction scheme that captures irregularities in languages and allow us to learn a much more compact lexicon that generalize well. So next we're going to see some examples of what kinds of variations we can compactly model. So many closely related lexical entries, for example, like the different forms of depart, have exactly the same semantic content. Although that they can appear in different syntactic contexts. And this pattern applies to arrive and arrives, and a flight and a flights. So it's gonna be a much more compact representation if we simply just factor out the word stems from the lexical entry, and then like learn a mapping between the word stem and the semantic content. And then we've seen like how to model the semantic content. Next, we're gonna see how to model the syntactic content. So words in the same class have the same syntactic patterns. So for example, the depart and arrive are both intransitive verbs that take a subject and then to complete the sentence. So if we abstract over the actual word and then the logical constant in the lexical entry, then we can just generate a template that works for all intransitive verbs. So the idea is like we can engineer a set of domain-independent and linguistically motivated templates that will work for each word class. And morphological inflection is another important regularity that can cause systematic variations. For example, when the transitive verb serve moves from the active voice to the passive voice, the order of the subject and object is reversed. So reversing the order of the variables in the lexical entry applies to all of the transitive verbs in passive voice. So it's going to be beneficial if we can encode that systematic morphological variation in the lexicon. And besides, there are external resources available that can help us recover word class information so that we can use that to restrict lexical entries to match the word class. This way that we can rule out lots of lexical entries that we could have learned wrong if there's no constraints at all. Based on all of the observations, we propose a new morpho-syntactic factor lexicon that has two advantages. So the first one, it models the linguistic variation, which helps recover the unseen word form. And second, the lexical entries are restricted using the word class information so that we rule out those context-specific lexical entries for rarely seen words. And we're going to demonstrate on two data sets and show that our approach generalized well, enables learning from less data, and with like all training data available, our system achieves up to 45% test error reduction. And other CCG induction approaches that's related to our work include some work that use hand-engineered templates for learning, but no explicit model of lexicon. And then the work that use that models some level of lexical generalization, but automatically induce the templates. And then also the work that we just heard of in the previous talk that use machine learning techniques to regularize a lexicon during learning. But our work is different from the previous approaches by using linguistic intuitions and external resources to define a much more constrained hypothesis space during parsing. So here's the outline for the rest of the talk. We're going to start with giving an example for semantic parsing, and then we're going to formally define our CCG lexicon. We'll talk about the experiments. We'll conclude the talk with future work. Okay, so a CCG grammar contains a lexicon that represents the meaning of the words. So each lexical entry encodes some text, and then its syntactic and semantic information. So given a sentence, the first step is we propose the lexical entries for each word and phrase in the sentence. And to produce a parsing step, we use the syntax as a guidance. So look at the syntactic category of the word various. It's looking for a n category to the right as an argument so that we can combine the two word various and cities to produce a new category for the subtree. And we repeat the same process until we build the entire parse. And the interpretation of the sentence will be the logical expression at the top of the parse tree. So here that we only show one possible derivation of the sentence, but of course there could be multiple meanings for each word and phrase, and then there could be different ways of combining them, so it's exponentially many parses potentially for each sentence. So next we're going to define the lexicon. So our morpho-syntactic lexicon is factored into three components, and each component modeled a different aspect of the systematic variation that we show in the motivating examples. So it includes a set of lexemes that pair the word stems with semantic constants. It has a set of linguistically motivated base templates that define the different syntactic roles of each word class, as well as a set of transformation functions that defines how to modify the base templates when a word is inflected. And then these three components work together to define the space of possible lexical entries that we can build for each input word. But note that both the set of base templates and the transformations are linguistic motivated and have been predefined. So the whole lexicon induction scheme, the problem is simplified to learning just a set of lexemes for each new domain. So we want to give a little bit detail on the process of designing the base templates. So the base templates are grouped into categories and indexed by their part of speech. We designed the templates that can be shared among all words in the same word class. So for example, the intransitive verbs take a subject to complete a sentence. The nouns are denoting a set of entities that satisfy a given property. And the prepositions are taking a noun phrase as an argument and then can modify nouns through conjunction. But we differ from the previous approach that also used engineer templates by considering a much wider range of linguistic constructions, including the Davisonian event for verbs, and then explicit treatment of relational nouns, etc. So if you're interested, please see the paper for the full list of base templates we use. And additionally, that we use the word class information to restrict the use of templates. So besides the base templates, the morphological transformations also encode the systematic variation when a word is inflected. We're not going to detail the motivation for every class, but here that we discuss two functions that does the transformation. So the first function describes how the verb templates can be modified when moving from the active voice to the passive voice. So syntactically, the majority of the templates stay the same, only changing the order of the variables, and plus the subject is now introduced in a propositional phrase, requiring us to change the NP to the PP for the argument. And then this function, we use the curly variable y to instantiate the rule to all of the verb with different transitivities. So y can take a different number of arguments for the verb. And the second transformation describes the present participle for verbs. So some verbs in the ing form can act as noun modifiers, as seen in the second sentence here. Departing can modify flights. So to model this variation, the transformation changes the root of the verb signature to the proposition category PP. So allowing the phrase departing from Boston to behave syntactically like a prepositional phrase and modify the flights. And again, like the previous transformation function, we use a curly variable to generalize it to other transitivities. Okay, so we've seen the basic setup of the lexicon. Now that we're going to walk through an example to show how we build a lexical entry given the lexicon. So the first step is we use a dictionary to map the word into a triple of word stem, its part of speech, and morphology. And we create such a triple for every possible entry of the word in Wiktionary. So for example, departing is going to be mapped to the stem depart, it's an intransitive verb, and then it's a present participle. So depart will be mapped to the logical constant depart by doing a stem matching in the lexeme set. And we pick the set of base templates engineered for the intransitive verbs, and then also the present participle transformation function. So the transformation function is going to map the verb signature to the PP category, and then we instantiate this template by applying the original word departing and the logical constant depart and produce the full lexical entry for the word departing. So now that I'm going to talk about the learning algorithm for the CCG lexicon. So given a weighted CCG grammar G which consists of a lexicon, a set of parameters, for each input sentence, the grammar produces a set of parses Y, and each parse is scored using a linear scoring function. And the best interpretation of the sentence is the logical expression at the top of the highest ranking parse Y hat. So the advantage of our lexicon induction scheme is it's a standalone procedure, which enables us to reuse an existing learning algorithm, and then with some minimal modification. So the algorithm, given a training set, xi being the sentence and then zi being the logical expression, the algorithm induces the lexicon, as well as learning a set of parameter theta for scoring the parses. So it visits the training example in an online fashion. And then for each training example, it uses a function genlex to expand the lexicon. And then here is where the modification comes to. Instead of mapping the substring in the sentence to a possible list of logical constants, we now map the word stem. And then the parameters are still updated using the perceptron. So we use two standard sets of features in the model. And the lexical features just look at the different aspect of the factorization in the lexical entry. And also the logical expression feature counts the co-occurring frequency of predicate argument pairs and predicate pairs. So let's revisit the generalization problem where arriving has never appeared in the exact ing form. With the factoring, we will be able to learn an entry in the lexeme set for arrive, and paired with the template, and then following the same procedure, then we'll be able to generate the correct lexical entry that's going to help recover the meaning of the sentence. So let's move on to experiments. We evaluate our system to benchmark semantic parsing data sets, GeoQuery and ADIS. We use the standard data splits. And then all of the systems are evaluated using exact match criteria. So that's the percentage of fully correct logical expressions. And then we initialize the features in the initial lexicon that consists of lexical entries for domain-independent function words and a list of NP words with positive weights. And then we give negative weights to templates that's required to model elliptical languages, negative weights so that we can discourage word skipping. So we compare our system to other approaches that have also reported on the same data sets, which includes the ZC05 and 07 that also use the hand-engineered templates, and then UBL, FUBL that automatically induce the templates, and then also a semi-supervised approach for GeoQuery that learns directly from question-answer pairs, and then as well as an unsupervised approach for ADIS. So this table reports the learning accuracy for the GeoQuery domain. We got the best number compared to other CCG systems, and then except that, DCS Plus achieves slightly better accuracy by using engineered C lexicon. For the ADIS domain, we outperform FUBL, which got the best number on the dev set by 7%, and then we improved the test accuracy by 8% compared with ZC7, which is the previous best system. And then in particular, the unsupervised approach, GUSP, although that it rivals with previous approaches, but we're still able to show that with careful use of supervision, we can open a pretty big performance gap. And we also studied the learning, the generalization performance brought by using the linguistic regularization during learning. So we compare our full approach with two ablated systems. The first one has no syntactic constraints, and the second one is trained with constraint but has no word stemming. And then also for reference, we compare with FUBL. So all of our systems generalize better than FUBL, especially with smaller training sets. And then our full system even achieves a comparable accuracy of FUBL with just a quarter of the training data. So we have demonstrated that significant performance gains can be achieved by introducing a more constrained, linguistically motivated grammar induction scheme. And then the linguistic intuitions that we use are domain-independent facts about languages, so that it makes it applicable to other semantic parsing applications. And we're also interested in studying how to constrain the hypothesis space with different level of supervision and possibly generalize it to other languages. Thank you.
So we have a lot of time for questions.
So another source of supervision you could have used is CCG Bank, where you've got something like 1 million words annotated with CCG lexical categories. Have you considered using that for supervision?
I'm sorry, what is the
CCG Bank, it's...
I think the advantage of using this approach is we also induce our own CCG lexicon, just to target it for the specific data sets. But potentially I think that it's possible that we can recycle some of the stuff learned in the CCG bank.
Okay, thank you.
So I'm wondering whether you looked at the differences between the two lexicons.
Compare with FUBL?
Yeah.
Yes, we have a table reporting the number of lexical entries and also the number of lexemes that we use in the two systems. And then I don't remember the numbers at the top of my head, but I think it's about like a 60% lexemes and then maybe 80% of the lexical entries. But those are only used in the last iteration of the testing round. So it's only the ones that appear in the highest scoring parsers.
Makes sense. Thank you.
So at the moment, when you recognize a morphological generalization, in many cases you're not reflecting that in the semantics, and that's obviously because of the data sets that you're measuring against. But have you thought about assigning a semantics to, for instance, the present and the past?
Yes,
those kinds of
actually, I think some of the morphological transformations actually have the specific modification on the semantic part. But because of the data set that we're using are querying a static database, so something like the tense and then aspect are not actually required to correctly understand the sentences. But potentially, yes, they do have modifications.
And are there any databases that you could use to flesh that semantics out?
I think something that's like maybe time sensitive that can use some kind of modification like that.
Okay. Well, thanks again, Adrienne.